Hello, today we will solve this mechanics paper from May 2023. It is Pearson Edexcel level 3 GCE. The first question is, two children Pat and Sam run a race along a straight horizontal track. Both children start from rest at the same time and cross the finish line at the same time. In a model of the motion, Pat accelerates at a constant rate from rest for 5 seconds until reaching a speed of 4 meters per second and then maintains a constant speed of 4 meters per second until crossing the finish line. Sam accelerates at a constant rate of 1 meters per second square from rest until reaching a speed of x meters per second and then maintains a constant speed of x meters per second until crossing the finishing line. Both children take 27.5 seconds to complete the race. The velocity time graph shown in figure 1 describes the model of the motion of each child from instant they start to the instant they cross the finish line together. Explain why the areas in the two graphs are equal. Find the acceleration of Pat during the first 5 seconds. Find in meters the length of the race. Find the value of x, giving your answer in 3 significant figures. So let's start this problem. Let's draw the model of the problem. Let's draw the graph of the problem. They both start together and finish the race together. This is Pat, this is Sam, and Pat reached a speed of 4 meters per second. Sam reached a speed of x meters per second. Pat reached a speed of 4 meters per second in 5 seconds. They both started from rest, so zero velocity at this. So what do we have to find? We have to explain why the areas under the two graphs are equal. Find the acceleration of Pat during the first 5 seconds. Find in meters the length of the race, and find the value of x. So we have to explain why area under the graphs is equal. We have to find acceleration of Pat. We have to find the total distance of the race, and we have to find x. Okay, x is the speed of Sam. Okay. So first things first, the area under the graph is same because is equal because both it's a race on a horizontal track. So we can assume that both Pat and Sam started from the same point and finished at the same point. So the total distance they covered should also be equal. So the total distance they covered is same because the area under the graph is the distance they covered, so the area under both the graphs will be same. So area under the graphs will be same. So that's why area under the graph is same, because the distance is same. So that's one thing. Now we have to find the acceleration of P. So the formula for acceleration is final velocity minus initial velocity divided by time. So what is the final velocity of Pat? Pat's final velocity is 4 meters per second. And his initial velocity is 0, and the total time for him to reach this velocity is 5 seconds. So his acceleration will come out to be 4 divided by 5, that is 0.8 meters per second squared. So that's the acceleration of Pat. Okay, so that's 0.8 meters per second squared. The third problem is we have to find the total distance. So again we will draw the graph. So we know that the area under the velocity time graph is the distance traveled. So if we measure the area under this graph, we can get the total distance traveled by Pat, which is actually the total distance of the race. So let's calculate this area. This area has two parts. Let's call this one A1 and let's call this A2. Okay, so A1 will be 1 by 2. This is the base here, and this is the altitude here. Okay, so 1 by 2 times 5 times 4. So this is 20 divided by 2, that's 10 meters. And A2 is simply a rectangle. So its area will be width into height. So it will be 5 into it will be 4 times the height times this width. Okay. So this width is 4 multiplied by 27.5 minus 5. 4 times 22.5. That's 90. Okay. So 90 meters. So the total area under this curve will be 90 plus 10 which is so the total area under the curve will be 90 plus 10, that is 100. So the total distance of the race will be 90 plus 10, that is 100. So that's the answer to part 2. Now we have to find x. We have to find x. So to find x, we need to find the total distance. With the total distance of the journey we have already found. The total distance of the race is 100 meters. We've already found in the previous answer. The total distance of the journey we have already found, which was equal to the total distance of the race was 100 meters. Okay. So now what we will do here, we will find we will devise an equation for distance. For we will find the equation for distance of the total race for Sam. We will find the equation for distance of the total race for Sam. So as you can see, this is the velocity time graph for Sam. It has the area under the velocity time graph. The area under the velocity time graph is the total distance covered. Okay. So this area is also divided into two parts. This part is let's call this A1. Let's call this part A2. Okay, let's call this part A1 and that part A2. So the total area will be A1 plus A2. So let's find the use the velocity time graph to calculate this area, to get an equation for this area. So let's call this point T1. Okay, and let's call this x velocity, x point V. Okay. So the area A1 will be 1 by 2 times T1 times V, and area A2 will be 27.5 multiplied by the area A2 will be 27.5 minus T1 times V. So it will be this. So it will be this minus this. It will give us the length multiplied by this height. So length into height. So it will be the area of the rectangle. So solving it, and we will get and it is equal to 100, which is the total area of the race. So solve it, simplify it, and we will get an equation for equation involving T and V. So let's solve it. 1 by 2 T1 V plus 27.5 V minus T1 V is equal to 100. Okay, so it will be 27.5 V minus 1 by 2 T1 V is equal to 100, and 27.5 V minus 1 by 2 T1 V minus 100 is equal to 0. So that's equation 1. Now what we need is another equation, because this equation is not gonna solve itself. We need another equation. Okay, so Sam starts from rest, so his initial velocity is u is equal to 0. His acceleration is, as given in the problem, is 1 meters per second squared. Okay, and the time he took to reach this x velocity, or let's v velocity, is t1, which is unknown. Okay, and v is also unknown. Okay, so we can use the first equation of motion, which is v is equal to u plus acceleration times time. Okay, so v is unknown. Okay, u is known, it is equal to 0. So v is equal to acceleration is known. Acceleration is what? Acceleration is 1 meters per second squared. So it will be 1 t1, or v is equal to t1. This is equation 2. We put this value in this equation, and we will get a quadratic equation. Let's do it. So this is the equation. Now it's a quadratic. Let's arrange it. Minus 0.5 v squared plus 27.5 v minus 100 is equal to 0. Now let's solve this quadratic for the values of v. So v is equal to minus 27.5, or let's first simplify and change signs. Now let's keep the signs same. Let's solve this quadratic. So it will give us two solutions to this problem, 3.92 and 51. So this velocity will have two possible values, 3.92 meters per second and 51 meters per second. We will ignore this value because in our original problem, as you can see, let me go to my previous slide. In our original problem, Pat's velocity was 4 meters per second, and velocity time graph of Pat and Sam. Sam's maximum velocity, which is x, was shown to be lesser than Pat's in the graph. So it is impossible. For Sam to have 50 meters cube 50. It is impossible for Sam to have a velocity greater than Pat. So the answer is logically ruled out. So the only logical answer is 3.92 meters per second. So that's the value of x. So that's it for this problem. So x is equal to 3.92, distance is equal to 100, acceleration we've already calculated, and area we've already answered. So that's it for this problem. Now we move to next question. A small stone is projected vertically upwards with a speed of 39.2 meters per second from a point O. The stone is modeled as a particle moving freely under gravity from when it is projected until it hits the ground 10 seconds later. Using the model, find the height of O above the ground, the total length of time for which the speed of the stone is less than or equal to 24.5 meters per second. State one refinement that could be made to the model that would make your answer part A more accurate. So let's say we are standing on a ledge, and the height of that and the point O is located on that ledge. We throw a stone upward. Then after some time the stone falls down. After reaching a certain height, starts falling down. Okay. The initial velocity with which we threw the stone upwards was 39 point, or Vi, as we say, Vi, or U is equal to 39.2 meters per second for the upward journey. Okay. From point O. The stone is modeled as a particle moving freely under gravity from when it is projected until it hits the ground 10 seconds later. The stone hit the ground 10 seconds later. So the total journey from here to top and back to ground is total time 10 seconds. Okay. So time total is 10 seconds. Some of that time was consumed while some of the time was used when the stone was moving upward, and the rest of the time was used when the stone was moving downward, was falling down. Okay. The total length of the time is so using the model, find the height O above the ground, the total length of time for which the speed of the stone is less than or equal to 24.5 meters per second, and state one refinement. So we have to find the height O. So let's break down the problem into small parts. So first we need to calculate the time from here to here, how much time it took for the stone to go from here to here. So to calculate that time, we will use V is equal to U plus AT. Final velocity is equal to initial velocity plus acceleration times time. In our case, in place of A, we will use minus G because it is opposing our motion. So we know the final velocity when it reaches the top is 0. 0 is equal to and we know the initial velocity, which is 39.2, and minus G times T. Okay, so T will be 39.2 divided by 9.8 be equal to 4. So it is the time it took for the stone to go from O to top of this height. Now we need to find the height from O to this. We need to find this height. Okay. So it will be UT. I've used VI instead of U here, so it's same. They both mean the same thing. So this height is 78.4 meters. Okay, and it took 4 seconds to reach this height. So the rest of the time, which is 10 minus 4, which is equal to 6 seconds, it took for the stone to fall down from this height to the ground. So we know what the velocity of the stone on this height will be. It will be 0, because whenever a body reaches a certain height, when we throw an object upward, it reaches a certain height, then it starts falling down, unless it has reached the escape velocity of the earth. So it has not reached the escape velocity of the earth, so it will reach a certain height, then will start falling down. So at that maximum height, its velocity will be equal to 0. So in that case, here the velocity or Vi will be 0. Vf we need to find. The total time is 6 seconds. So and the acceleration is G, and it's positive G. Okay, so final velocity will be Vf is equal to Vi plus Gt, which is equal to 0 plus 9.8 times 6, which is equal to 58.8 meters per second. So the total height, the total distance from here to here can be found using the third equation of motion. 2gs is equal to vf square minus vi squared. Okay, we have found we know vi is equal to 0. Vf we have just found, which is 58.8. Gravity g we know is 9.8. So s will be the total distance from of O from ground. Okay, it will be s will be the total height of O from so we can find the total height using this. So s will be the total height that stone reached from the ground. Okay, s will be the total height the stone reached from the ground. So basically it becomes something like this, which is equal to 176 point, sorry, which is equal to 176.4 meters. So s is 176.4. so the total height of point O from ground is 176.4 minus 78.4, which is equal to 98 meters. So the point O is 98 meters high. So that's the answer to part 2. Now that's the answer to part A. Let's find the total time the speed of the stone remained below 24.5. Okay, the speed of the stone remained below 24.5. Now the stone was projected with the speed of 39.2. Okay, the stone was projected with the speed of 39.2. So we can use the first equation of motion to find the time its speed was above 39.2. Okay, so Vf is equal to Vi plus negative g times t. We will use negative g because it is opposing our motion. So Vf is we need to know the time its speed remained above 24.5. So Vf is 24.5, Vi is 39.2 minus g is 9.8 times t. We need to know this time. We know the total time, which is 4 seconds. So let's see how much we get. So 24 minus 39.2, that's 1.5 seconds. That's t is equal to 1.5 seconds. So during our upward journey, our velocity remained greater than 24.5 for 1.5 seconds, which means it remained less than 24.5 for 4 minus 1.5 seconds, because we know that the total time for upward journey was 4 seconds. So 4 minus 1.5 is equal to 2.5 seconds. So during upward journey, the velocity remained less than 24.5 for 2.5 seconds. That's one part. Let's write it somewhere. Now during the downward journey, it started accelerating from 0 and reached a certain velocity. Okay, we want to know the time its velocity was below 24.5 seconds. So we will again use the first equation of motion to find the total time its velocity remained less than 24.5 seconds. So Vf is equal to Vi plus At. Okay, in place of A we will use positive G because now it is supporting our Vf is equal to Vi plus Gt. Now final velocity is 24.5. Initial velocity is 0 and the acceleration is 9.8 and time is time. So we get 24.5 divided by t, 24.5 divided by 9.8, that is equal to 2.5 seconds. So the total time the velocity remained above remained below 24.5 second 24.5 meters per second is this plus this, which we've already calculated. So total time is 2.5 plus 2.5, which is equal to 5 seconds. So total time of the journey during which our velocity remained below 24.5 meters per second is 5 seconds. Okay, that's how you solve this. Now the one refinement that could be made to the model that would make our answer more accurate is if we should there should be some accounting for air resistance, because if there is air resistance, the stone would not reach the same height, it would reach less high, so it would make our answer more accurate. So let's move to the third question. A car of mass 1200 kg is towing a trailer of mass 400 kg along a straight horizontal road using a tow rope as shown in figure 2. The rope is horizontal and parallel to the direction of motion of the car. The resistance to motion of the car is modeled as a constant force of magnitude 2 newtons. The resistance to motion of the trailer is modeled as a constant force of magnitude 2 newtons. Constant force of magnitude r newtons. The rope is modeled as being light and inextensible. The acceleration of the car is modeled as a meters per second squared. The driving force of the engine of the car is 7400 newtons, and the tension in the tow rope is 2400 newtons. Using the model, find the value of A. In a refined model, the rope is modeled as having a mass, and the acceleration of the car is found to be A1 meter per second squared. State how the value of A1 compares with the value of A. State one limitation of the model used for resistance to the motion of the car. So I'm going to draw this on my whiteboard. So I'm going to draw this on my whiteboard. There's this trailer. There is this rope, and there is this car. The car weighs about 1200 kgs, and the trailer weighs the trolley or trailer, whatever, it weighs about 400 kg. The car faces about resistance to the car 2R and resistance to the trailer 1R. The driving force of the engine of the car is 7400 newtons, and tension in the tow rope is 2400 newtons. Engine force and tension in the tow rope 2400 newtons. We have to find the value of A, the rate of the acceleration of A. We have to find the x value of A. So let's dig into it. So let us assume that the car and the trolley are moving at the same speed, so they will naturally have the same acceleration. Okay, so if we try to consider them as a one rigid body with having two masses, so we can devise an equation of motion for each. For example, the equation of motion of the car will be something like, for example, the car has a mass 1200 kg. So the car has a mass of 1200 kgs. Okay, and the engine of the car is generating a force of 7400 newtons. Okay, these, now let's make an equation where we balance out the forces on the car. So the car is moving with acceleration a. Okay, this acceleration a is applied on the mass of the car, which is 1200 kgs. Okay, this is the resultant force of the this is the resultant force of the car with which it is moving. So this is the resultant force of the car with which the car is being accelerated. Now the force is applied by the engine. The force is being applied by the engine. So the total force of the engine is 7400 newtons. And we have to subtract from this engine force the force of the tension on the trailer. Now the tensile force on the car is negative, because it is because the car is driving the trailer, not the trailer driving the car. Okay, so with the perspective of the car in mind, that tension force on the car is slowing it down. Okay, so there should be a negative sign with it. Okay, so that is 2400 newtons with a negative sign. Okay, so this is the equation of force. When we balance out all the forces on the car, this is the equation. Okay, so if we simplify this equation, we can very easily get the value of A. Okay, so one more thing I forgot about it. Also, there is a negative resistance force on the car as well. Okay, negative resistance force on the car as well, which is minus 2R. Okay, so yes, this forms an equation which is something like this. It's 5000 plus minus 2R 1200 A. So this is equation 1. Okay, this is equation 1. Now for the trailer, and a similar equation will be, we will derive a similar equation for the trailer. We know the weight of the mass of the trailer is 400 kgs. We know that the acceleration of the trailer and the car will be same. Okay, and we know the tensile force which is pulling the trailer. Okay, okay. Also, we know the resistance on the trailer. So the balance force equation for the trailer will be, this is mass of the trailer, which is 400 times A. This is the net force which is driving the trailer. Okay, net force. Okay. Now what are the other forces being applied on the trailer? What are the other forces? Because the net force which is accelerating the trailer in the right direction is the sum of all the forces acting on the trailer. So the tension which was being applied by the tow rope of the car is also the force that is pulling the trailer in the rightward direction. When we were discussing the tension in reference to the car, it was a negative force, but in reference to the trailer, because it is a pulling force, it is a force that is causing the trailer to move. Okay, not causing it to slow down. So it will be positive when it comes to the trailer. Okay, so the tension of the trailer of the tow rope will be its value is 2400 newtons. Okay, so it will be positive force, will be a positive force. So positive 2400. Okay, the negative forces on the trailer are the resistance force, which is minus 1R. Okay, so that's all there is to it. So these give us two equations. Okay, these give us two equations. We will solve these equations to get a value of A and R. Okay, so this will be our solution to our problem. So let's solve them. So it will be like R is equal to 400 A plus 2400. Okay, that'll be R. So we put the value of R here. Okay, what we get is, okay, so it'll be minus 800A, plus 800A minus 4800 plus 5000 is equal to 1200A. Okay, so that will be 40 minus 4800 plus 5000 is 200. Okay, and minus 800 plus 1200 is 400. Okay, so A will be 200 divided by 400, that is 0.5. So A is equal to 0.5 meters per second squared. So that's the answer. So that's the value of acceleration which we had to find. So that's it. We can improve this model by considering the resistance, the kinetic resistance of the wheels and the power losses of the engine in the drive shaft. Okay, so these things were not considered. Also we can improve our model by considering that the rope behaves something like a stretchy spring. Okay, if we are to consider that the rope has some kind of extension going on with it, then we can say that the acceleration A1, the question as asked in the question, the acceleration A1 will be slightly greater than acceleration A1 will be slightly greater than A. A1 will be slightly greater than A because A1 is the driving acceleration, not the driven acceleration. So the cause will always precede the effect. The cause will always come before and after the cause comes the effect. So naturally A1 will be slightly greater than A. Whenever the rope will always reach first, the trailer will always reach second. So that's why A1 will be greater than A. Also some force will be absorbed in the rope as well. Okay, so that's the answer to this question. Let's move to the last one. Now here we have a model given. V is equal to 15 minus t square minus 2t. A particle moves along a straight line such that at time t seconds, t equal to 0, after passing through O. The velocity of particle is modeled as 15 minus t square minus 2t. Verify that p comes to instantaneous rest when t equal to 3. Find the magnitude of the acceleration of p when t equal to 3. Okay. Find the total distance traveled by the particle in the interval 0 to t equal to 4. Okay. So what we have been given here is an equation for velocity which is equal to minus t square minus 2t plus 15. Right. We have been given the equation of velocity here. Okay, we have to prove that when t is equal to 3, the particle comes to instantaneous rest. When we say the particle comes to instantaneous rest, which means that v becomes equal to 0. V is equal to 0. So if the particle does come instantaneous, reach instantaneous rest, or does come to instantaneous rest, or becomes stationary, then when we put t equal to 3, t equal to 3 must be a solution of this equation. Okay, t equal to 3 must be a solution of this equation. So if we put t equal to 3, if the solution comes out to be 0, then it means that the at t equal to 3 the velocity is equal to 0. So we will put t equal to 3 in this equation to see if it comes to 0 or not. So 3 squared minus 2 times 3 is equal to 15 minus 9 minus 6, which is equal to 0. So yeah, this is a solution. This t equal to 3 is a solution of this equation. It means that the body does actually come to rest when at t equal to 3 seconds. Okay. Now the second part, find the magnitude of the acceleration of p when t equal to 3. So we have to find the magnitude of acceleration of p when t equal to 3. We know from calculus that velocity is a derivative of distance over time. Okay, distance over time. Okay, we also know that acceleration is the derivative of velocity over time. Okay, acceleration is the derivative of velocity over time, or acceleration is the double derivative of distance over time. So right now this part of information is going to be useful for us. So we're gonna erase this one. So we know that acceleration is a derivative of velocity with respect to time. So what it means is that whenever the speed of or velocity of an object changes with in some time interval, it undergoes some kind of acceleration. Okay, so acceleration is dv over dt. So we will simply take the derivative of this equation, which is 15 minus t square minus 2t d over dt. Okay, we take the derivative of this and we will get the derivative of 15 is 0 and derivative of t square is minus 2t, because there is a negative sign here, and derivative of minus 2t is minus 2. Okay, so we have to find the acceleration of the p when t is equal to 3. When t is equal to 3, we have to find the instantaneous acceleration when t is equal to 3. So what we do, we differentiate it at t equal to 3. So what we do, we put t equal to 3 in this equation. Okay, so minus 2 times 3 minus 2 is minus 6 minus 2, that's minus 8. So it's minus 8 meters per second squared. Okay, so the acceleration at the instant t equal to 3 is minus 8 meters per second, which clearly indicates that this is a deceleration. This is a deceleration. The body was slowing down, and the body slowed down near instantaneously. Okay, so find the total distance traveled by p in the interval 0 to t. So I'm gonna clear the whiteboard a little bit, write the answers and clear the whiteboard. So we have to find the total distance traveled from the interval 0 to 4 seconds. 0 to 4 seconds. We have been given the equation of velocity. V is equal to 15 minus t square minus 2t. So we know that the derivative of velocity is acceleration, but we also know that the integral of velocity is the total distance covered. Okay, the integral of velocity is the total distance covered. So what we do, we integrate from 0 to 4 and we will get the total distance traveled. Okay, so we integrate this velocity from 0 to 4 and it will be the total distance. So 15 times 4 is 60 minus 64 divided by 3 minus 16 minus 0. Okay, so 60 minus 64 by 3 minus 16. Okay, so 60 minus 64 by 3 is so the total distance is 68 by 3 68 divided by 3 meters. The total distance traveled is 68 divided by 3 meters. That's it. So this is the final question. Hit like and subscribe, and if you have any questions, do let me know. Thank you.